Consider a modern marvel of engineering, a colossal container ship, its deck stretching longer than 4 football fields. Deep inside its steel heart beats an engine the size of a 3-story building, generating over 100,000 horsepower. It is one of the most powerful moving objects on the planet, and yet, it deliberately sails slower than a passenger liner from the 1950s. Have we gone backward? Is this a failure of technology? The answer is no. This is a story of surrender. There is a fundamental law of the ocean that punishes speed with such brutal force that even our most powerful machines must bow to its will. This isn't a simple story of drag. It's a hidden war against physics, where the water itself fights back, eroding propellers, creating destructive vacuums, and demanding a ruinous price in fuel for every extra knot of speed. This is why, on the sea, speed has a cost that is almost always too high to pay. To understand this surrender, we must first look at the most visible way the ocean fights back. A ship moving through the water isn't just cutting a clean line. It is a massive object displacing a colossal weight of liquid. It shoves the water aside, and that displaced water has to go somewhere. It goes up, creating a wave at the bow, and then another at the stern as the water rushes back to fill the void. This wave system isn't just a pretty wake, it is pure energy, stolen directly from the ship's engine. The bigger the waves, the more energy is being bled away from pushing the ship forward. Naval engineers have a name for the point where this energy theft becomes catastrophic: hull speed. Imagine a ship accelerating. Its bow wave and stern wave move along with it, their crests a certain distance apart. As the ship goes faster, the wavelength gets longer. At a specific velocity, a critical point is reached. The ship's own length fits perfectly between the crest of its bow wave and the crest of the wave at its stern. The ship is now sailing in a permanent trough, a hole in the ocean of its own making. To go any faster, the ship must do something physically absurd. It has to climb its own bow wave. It's trying to drive up a perpetual liquid hill that grows steeper and taller the harder the engine pushes. Beyond this hull speed, almost all the additional power from the engine isn't used to increase speed. It's wasted on making the waves bigger, digging the hole deeper, and making the hill steeper. This is the ocean's first and most fundamental tax on speed. It's a wall, not of concrete, but of pure physics, a point of brutally diminishing returns. But what happens when engineers try to brute force their way over this wave wall with even more powerful propellers spinning at incredible speeds? They discovered that the water fights back in a far more insidious and destructive way. It's a phenomenon that doesn't just waste energy, but actively eats away at the very metal of the ship, turning the water itself into a weapon. When engineers pushed propellers to spin faster and faster, trying to break through the wall of wave resistance, they ran into an even more destructive opponent. This enemy wasn't visible. It wasn't about simple friction. It was a phantom menace born from the physics of pressure, a phenomenon known as cavitation. Think of a propeller blade slicing through the water. The front face pushes water, creating high pressure, but the back face, the suction side, does the opposite. As it moves, it leaves a region of extremely low pressure behind it. If the propeller spins fast enough, this pressure can drop so low that the water, even in the cold ocean, does something extraordinary. It boils. This isn't boiling from heat, it's a cold boil caused by a vacuum. The water molecules spontaneously rip apart, forming tiny, transient bubbles of water vapor. These bubbles are harmless as they form. The true violence happens when they die. As the propeller blade continues to turn, these bubbles are swept into areas of higher pressure just a fraction of a second later. In this new environment, they can no longer exist. They don't gently pop, they implode. They collapse on themselves with catastrophic force. This collapse is incredibly violent. It creates a shock wave and a microjet of water, a tiny focused spear that can strike the propeller surface at hundreds of meters per second. Naval engineers describe this process as being hit by millions of microscopic hammers, over and over, every single second. A single bubble is insignificant, but billions of them, imploding continuously, have a devastating cumulative effect. They physically blast away metal. Propellers made of the most advanced, hardened bronze alloys end up looking like they've been eaten by acid, their surfaces pitted, eroded, and eventually destroyed. Pushing for more speed doesn't just demand more fuel, it actively consumes the ship's own propulsion system. This created a seemingly unbreakable paradox. The very act of generating more thrust to go faster was destroying the source of that thrust. This destructive cycle seemed like a fundamental dead end. But what if, instead of trying to prevent these millions of tiny destructive bubbles, military engineers decided to embrace the idea? What if they could create one single, giant, stable bubble to wrap an entire vehicle in, effectively making it fly underwater? This seemingly sci-fi concept led to one of the fastest and most terrifying underwater objects ever built. This destructive force of cavitation seemed to present an absolute limit. But Cold War military strategists, faced with this problem, asked a radical question. What if, instead of fighting the bubbles, you intentionally created one enormous, stable bubble and wrapped an entire vehicle inside it? This is the principle of supercavitation, and it led to the creation of one of the most astonishing and feared underwater weapons ever conceived, the VA-111 Shkval torpedo. The Shkval is designed not to minimize cavitation, but to maximize it. On its nose is a specially shaped disc called a cavitator. As the weapon launches, this disc forces the water to flow around it so quickly that it instantly vaporizes, creating the beginning of a bubble. At the same time, a powerful solid-fuel rocket engine ignites, not only providing immense thrust, but also venting its hot exhaust gases into this initial vapor pocket. The gas inflates the bubble, creating a large, stable envelope, a cavity, that encases the torpedo's entire body. The result is a vehicle that is no longer moving through water. It is flying through a pocket of gas, with only its nose and tail fins touching the liquid. Freed from the crushing grip of water resistance, the Shkval achieves speeds that sound like science fiction. According to open sources, it can travel at over 200 knots, more than 230 miles per hour. That is 3 to 4 times faster than a conventional torpedo. But this incredible speed comes at a crippling price. The Shkval is a brute force solution with severe limitations that make it useless for any kind of commercial or passenger travel. First, its rocket engine is monstrously inefficient, burning through its fuel in a matter of minutes, giving it an extremely short range. It's a drag racer, not a long-distance hauler. Second, it is almost impossible to steer. A rudder needs a dense medium like water to push against. Inside its own gas bubble, the Shkval's control surfaces are largely ineffective. This makes it, for all intents and purposes, a straight-line weapon. Finally, it is the opposite of stealthy. The process of generating a supercavity and firing a rocket engine underwater is incredibly violent and loud, announcing its presence to every enemy sensor in the ocean. It is a thunderous battering ram, not a silent assassin. So, even this most extreme technological solution proves to be a dead end for practical travel. It's a spectacular but highly specialized military tool. But even if we could somehow solve the physics of waves and the material science of cavitation, all ships, from the fastest warship to the slowest tanker, run into a final, unforgiving wall. This wall isn't made of water or vapor, it's made of numbers on a balance sheet, and it is the most brutal barrier of all. We have seen the physical walls the ocean erects against speed, the wall of wave resistance where a ship must climb a hill of its own making, the destructive wall of cavitation where the water itself eats away at metal, and the spectacular but ultimately impractical dead end of supercavitation. But even if engineers could perfectly solve all of these problems, they would still smash into a final and far more unforgiving barrier. This wall isn't made of physics. It's built from numbers on a balance sheet, and it is the most absolute limit of all. The relationship between a ship's speed and the fuel it burns is not a straight line. It is a steep, punishing curve. Naval engineers work with a principle often called the cubic law. In simple terms, the power needed to overcome water drag increases with the cube of the vessel's speed. This means to double your speed, you don't need double the power. You need something closer to 8 times the power, and therefore, roughly 8 times the fuel consumption per hour. Each additional knot of speed costs exponentially more than the one before it. This is the cold, hard logic behind slow steaming, and it directly answers the paradox of our powerful but slow container ship. For a modern shipping giant, fuel is by far the single largest operating cost, often accounting for over half of the entire voyage's expenses. At a design speed of 24 knots, a large vessel might burn over 150 tons of fuel per day. By deliberately reducing that speed to 20 knots, a drop of less than 20%, the ship's operator can cut daily fuel consumption by 40% or more. On a single trip from Asia to Europe, this decision can save millions of dollars. The ship isn't slow because our technology has failed. It is slow because it is a finely tuned instrument of economic efficiency. This stands in stark contrast to the fast passenger liners of the past. They were symbols of national prestige, often built with government subsidies in an era of cheap oil. Their goal was to sell speed and luxury. Today's cargo ship has a different master, the global supply chain. Its cargo doesn't applaud a record-breaking crossing. The only metric that matters is the final cost to transport each container. The practical limit is not only physics, but cost. We've now seen the wall of waves, the destructive fury of cavitation, the dead end of extreme solutions, and the unbreachable wall of economics. These are not 4 separate problems. They are all symptoms of a single, fundamental truth about the sheer density of water. It is here that we find the final answer to why the ocean punishes speed far more brutally than the air ever could. So we arrive at the final truth: the wall of waves, the self-destructive fury of cavitation, the dead end of supercavitation, and the unforgiving wall of economics. These are not 4 separate problems. They are a cascade of consequences, an interconnected system of energy loss where each problem feeds the next. The struggle to overcome wave resistance forces engineers to add immense power. That very power, channeled through a propeller, creates the low-pressure voids that trigger cavitation. The cavitation then eats away at the machine, creating a physical limit. And even when military technology brute forces a way around this with a gas bubble, the solution is wildly inefficient and impractical. This entire chain of physical destruction is mirrored by the crushing economic reality of the cubic law, where every attempt to push harder is punished with an exponential increase in fuel consumption. But why? Why is the ocean so much more punishing than the air? The ultimate answer lies in a single, fundamental property of the medium itself: its density. Water is over 800 times denser than the air at sea level. Moving an object through a fluid means you must physically displace the mass of that fluid. The energy required to do that is directly related to its density. Pushing aside a cubic meter of water demands orders of magnitude more energy than pushing aside a cubic meter of air. This is why a commercial airliner can cruise efficiently at over 500 miles per hour, while the fastest naval destroyers struggle to sustain 35 knots. The sky is a near vacuum compared to the ocean. The energy penalty for speed in water is not just higher, it is on an entirely different scale of reality. The ocean does not forgive. And this brings us back to our colossal, slow-moving container ship. Its deliberate pace is not a sign of technological failure. It is the signature of a profound success. It represents the triumph of a holistic understanding, a perfect balance of physics and economics. Naval engineers and shipping lines have not surrendered to the ocean. They have learned to respect its power. They have understood that in this war against drag and density, the most intelligent strategy is not to fight harder, but to calculate the monumental cost of the battle and choose not to fight it at all. The slowness of a modern ship is a choice, a wise, calculated, and incredibly profitable choice, dictated by the unforgiving laws of the planet. It is the ultimate expression of efficiency, where the greatest victory is achieved by consuming less, moving smarter, and acknowledging the absolute power of the sea.